In the previous videos, we have already discussed what is upper bound, lower bound, what is least upper bound, what is greatest lower bound, what is also maximum and also minimum. Now, what is a supremum and infimum of a set? Let A subset R. R is the subset. R is the set of real numbers. In Venn diagram, this is R, this is S. Let S subset R. Then the supremum of the set S is denoted by the symbol SUPS, and it is defined as supremum of S equal to the least upper bound of S if S is bounded above, and infinity if S is not bounded above. That means in case of the bounded set, the supremum coincides with the least upper bound. Similarly, the infimum of the set S is denoted by INFS, and it is defined as infimum of S equal to the greatest lower bound of S if S is bounded below. That means if the infimum of S is equal to the greatest lower bound of S if the set is bounded below, and infimum of S equal to minus infinity if S is not bounded below. This is the definition. So, the supremum of X belongs to R such that X greater than A and A is any real number is equal to infinity. And infimum of S equal to X belongs to R such that X is less than A, where A is any real number that is equal to minus infinity. Supremum of R equal to plus infinity and infimum of R equal to minus infinity. Similarly, in case of the intervals. This is about the supremum and infimum of a set. Now we prove the most important theorem. This is also last theorem of this chapter. What is the relation between the supremum and infimum? There is a most important theorem. Dear students, now we will start the most important theorem, which relates what is the relation between supremum and infimum. Let alpha belongs to R. Alpha is a real number and S is any subset of R. Then prove that alpha into supremum of S equal to supremum of alpha S if alpha is greater than 0 and infimum of alpha S if alpha is less than 0. That means we consider two types of sets. One is one is S, another is alpha S. Let S is a set. Alpha is a real number. The alpha S is another set. This is alpha S. The alpha S is defined as alpha S equal to alpha X such that X belongs to S. That means alpha times S means alpha times each element of the set S. That is alpha S. Suppose S is equal to 1, 2, 3, 4. 5 is my scalar alpha. Then 5S is equal to 5, 10, 15 and 20, like that. We define alphas when S and alpha are given. Now alpha times supremum of S equal to supremum of alpha S if alpha is greater than 0. Alpha times supremum of S equal to infimum of alpha S if alpha is less than 0. Where alpha is any real number and S is always subset of the set of real numbers. That means S is a subset of R. In Venn diagram, this is a alpha, this is R, and this is S. Let S is unbounded above and alpha is greater than 0. Alpha is greater than 0 and the set means that may be bounded above, may be unbounded above. Suppose the case 1, S is unbounded above. Since S is unbounded above, supremum of S equal to infinity. And supremum of alpha S, that is equal also infinity, because alpha is greater than 0. Which implies alpha into supremum of S equal to supremum of alpha S. That means this is true when S is unbounded above and alpha is greater than 0. This is case 2. Let S is bounded above and alpha greater than 0. Since S is bounded above and alpha is greater than 0, then alpha S is also bounded above. Since R is complete, then a set which is bounded above is must have the least upper bound. Since R is complete and S and alpha S has the least upper bound, that means it has a supremum. Let B is equal to the least upper bound of S, that is equal to the supremum of S. Similarly, C is equal to the least upper bound of alpha S, that is equal to supremum of alpha S. Since B is the least upper bound of S, then every element of the set S is less than equal to B, X less than equal to B for all X belongs to S, which implies alpha X less than equal to alpha B for all alpha X belongs to alpha S, because alpha is greater than 0. When you multiply a scalar in an inequality, the inequality remains intact. So every element of alpha S is less than equal to alpha B. By definition of upper bound, alpha B is an upper bound of alpha S. Since C is the least upper bound of alpha S and alpha B is any upper bound of alpha S, the least upper bound must less than equal to any upper bound C less than equal to alpha B. This is equation number 1. Now C equal to the least upper bound of S. Least upper bound of alpha S means every element of alpha S is less than equal to C, means alpha X less than equal to C, which implies X is less than equal to alpha inverse C for all X belongs to S, which implies alpha inverse C is an upper bound of S. Since B is the least upper bound of S, alpha inverse C is any upper bound of S, the least upper bound must less than equal to any upper bound, means B less than equal to alpha inverse C, which implies alpha B is less than equal to C. This is equation number 2. From equation 1 and 2, we have alpha B is equal to C. Alpha into supremum of S equal to supremum of alpha S if S is bounded above and alpha is greater than 0. This is case 2. Next we will prove alpha into infimum of S equal to infimum of alpha S if alpha is greater than 0, and alpha times infimum of S equal to supremum of alpha S if alpha is less than 0.